My pleasure to introduce Pascal. Pascal is, in some sense, my contemporary, meaning that he did his PhD about the same time I did, except that he's younger, fitter, more dynamic, smarter, and whatever, in all kinds of ways. So I know he was at SRI for some time, and then did his PhD under Olivier, right?
Yeah.
And Olivier Faugerat. If you don't know Olivier Faugerat, that's as much of a sin as not knowing who Tom Binford is. So you all really have to do your homework. And I think subsequently was a SRI for some more time before he went back and took his position at EPFL. I know back in the days when I first knew about his work, he was working on similar topics that I was, which is motion tracking, 3D reconstruction, stereo, and I guess it's this topic. But more recently, somehow I keep thinking about you in the context of brain images or MRI or something. Kind of moved on to more interesting applications of, I think, vision, but by and large, technically focused on very similar things as he was doing. Anyway, without further ado.
So actually, since you mentioned Olivier, this is kind of a throwback to the 90s and projective geometry. But at the time, we were doing rigid things. And actually, Olivier famously stated that the vision problem was solved. I don't think, I beg to differ with the master. But still, what was started then has continued, and we got involved into trying to model deformable surfaces. So we've done quite a bit of stuff with 2D surfaces. So actually, I kind of like this one, so I'll show it. Here's a t-shirt. It's just a plain t-shirt sitting on the table. And this is a very important animal. It's a platypus from the Jura Mountains in Switzerland. So, because he's carrying the little flag. And what we're going to do is we have a webcam. We are taking an image of the t-shirt, and we are pasting the platypus on the t-shirt. And I think it's reasonably well done. It moves. I mean, the inserted platypus is deformed correctly as the t-shirt deforms. It's relighted correctly. And by and large, it can handle occlusions. I mean, you'll see there are a few places where you can see that it's not quite right. So there's still a bit of work to be done, but mostly it's not too bad. So that was fun stuff. But it was done strictly in 2D. Here we are only computing the 2D deformation of the t-shirt to do this, to deform this accordingly. So having done that, the next question was, can we do that kind of thing in 3D? Meaning, I have an image of this object, which is a scarf, and now I have a second image. So I'm going to call that the reference image. I'm going to call this the input image. And can I infer the shape of this given this image and the fact that I actually know the shape in its first image? It doesn't actually have to be flat. It just has to be known. And the answer, of course, is what I'm going to talk about. Yes, you can. Yes, we can. Back to Obama. Got in trouble lately, so maybe I shouldn't go down that tack. So more formally, so the problem we are trying to solve is I have what I've called this reference image. I have the reference shape, and I have the input image. And what am I? I'm assuming I have a calibrated camera, so I know the intrinsic parameters of my camera. And I'm going to compute correspondences. So I'm going to use SIFT or anything you want to compute correspondences from here to there. And because I have the reference shape, these really are 3D to 2D correspondences. Correspond with a 3D shape and a 2D image. And what I want, the unknown, what I'm trying to compute are the 3D vertices, the coordinates of the 3D vertices of that mesh in that image. This is X is what I'm going to try to recover. So of course we all know that this is a very ambiguous problem because many 3D shapes can have the same projection. So here are two of the simplest cases of ambiguity, the scale ambiguity, where a small shape close by gives you the same projection as a big shape far away. Here is one that's slightly more subtle. something that's concave and convex. Actually, it doesn't give you exactly the same projection. But if the camera is far enough, or worse, if it's orthographic, then it does. So this is also ambiguous. And these are only two cases. There are lots and lots of these things. So we have an ambiguous problem to solve, an ill-posed problem to solve. We are going to need assumptions, models, something. And the whole focus of this work is to try to see what are the minimal assumptions we can make in order to make this well-posed and get a solution. So first, before I talk about the assumptions, I'd like to show you that there is a linear formulation for this problem. A very simple one, actually. And so the context is, I have a calibrated camera, so I have my matrix of intrinsic parameters, and I'm going to do all the reasoning in the camera referential. So translations and rotations that will be with respect to the camera. So my unknown, as I said, are the 3D coordinates of the vertex V1 to VNV. Here are the vertices of the mesh. Each one has 3 coordinates. And what I have, are correspondences. So I'm sorry it doesn't come up very well on the slide. I don't think you can see it. But what we have here is a facet of the mesh with 3 vertices. And we have a point in the middle of the mesh somewhere that projects to the image. So this point in the middle here can be expressed in terms of its barycentric coordinates in the facet to which it belongs. And the projection equation is this. I mean, just you write it in simple projective geometry. And each correspondence gives you one of these, where the unknowns, again, are the 3D coordinates of V1, V2, V3. The barycentric coordinates are known because you know what point you're talking about. So, in fact, what that gives you are 2 linear equations. Because you can eliminate you have 3 coordinates, you can eliminate the k, you get 2 linear equations per correspondence. And so what you can do is you take all these linear equations, you stack them up, and what you get is a very simple system. You get a matrix M that summarizes all your correspondences, and you're looking for x, the vertex of all coordinates, as mx equals 0. Done. Well, no, not quite, because the matrix M is very, very ill-conditioned. In fact, if you compute its singular values, the singular values are going to look like this, and that's systematic. That's pretty much for all M matrices we've tried, so all set of correspondences, where what happens if you have n vertices in your mesh, you have 3n unknown, 1 for each coordinates. And you have 2n non-zero singular values, and n values that are not exactly 0. There's only one that's exactly 0 because of the scale ambiguities. But you have n minus 1 that are very, very close to 0. And why? I mean, it's actually very easy to understand. Essentially, having the correspondences forces the vertices to move along known lines of sight. So which means that for each vertex, 2 of the degrees of freedom are actually well constrained. But small variations along the line of sight don't change the projection that much. And so it's very poorly constrained, and these small singular values and the ambiguities we've talked about. That's how they show up at this problem. So what we are going to have to do is to add constraints so that we can solve this, even though there is the null space of that thing is of dimension n. So as it turns out, a very good way to do this is to impose inextensibility constraints. What I don't really want to do too much, I'll do it a little bit, I'll show you why, is to assume that the surface is really smooth. Because that's what's normally done. And the problem with that is that if you really impose enough smoothness to make this well posed, you limit yourself to really smooth deformations. I'd like to try to avoid that, And eventually, I want to be able to model sharply folding surfaces. So instead of doing that, what we are going to impose a constraint that says that the surface, the distances between vertices remain fixed, which is one way of saying that the surface is inextensible. And the way we are doing this, there are several ways we are doing this, but one way to do this is to say that, okay, we are looking for the solution of the system mx equals 0, where the null space is of dimension m. So we find the eigenvectors, or the singular vectors that correspond to the small eigenvalues, and essentially, to within a pretty good approximation, any solution x, which is a weighted sum of these small singular value singular vectors, will give you a projection that's roughly correct. So you can express x as a weighted sum of these singular vectors, and the unknown of your problem now become the n weights that you give to these small eigenvectors. And by the way, I don't know how many of you were at the conference in Chennai, but Aaron presented an algorithm for doing animation and minimizing series of quadrics of low rank. And essentially, I think it's the same idea, except in this case, we have only one level. We didn't have the... so anyway, so we have x, which is a weighted sum of these guys, and we want to write that the distances between vertices remains constant. So that gives us a quadratic constraint, 1 per edge. The problem is the meshes we are dealing with, say typically have 30 by 40 vertices, that's n is 1200. I'm not sure exactly how many edges that is, but that's a lot of edges. And there are ways for solving system of quadratic equations, but try to give that many to MATLAB and see what happens. Basically, it dies a miserable death. It's much, much too big, and we can't do it. At least maybe some smart Russian mathematician has found a way, but we don't know of it. So we can't quite do it this way. So what we have to do is essentially something I said we didn't want to do, but in this case we have to do it anyway, is to reduce the number of degrees of freedom. And one way to do this is to do PCA. And so essentially what you can do is if you have a kind of object that, for example, has a known physical properties, or you have a training database, you can get a number of deformed samples of your object, do PCA on this, and express your shape X as a rest shape plus a weighted sum of modes, of deformation modes, which in matrix form you can write this way, where your unknown now are the modes. So if you use relatively few modes, basically what you're doing is smoothing typically, but you're also reducing the number of degrees of freedom. And one way actually to do this, what we have found that was very effective, in some cases, if you're dealing with a physical object for which you have a stiffness matrix, you can actually compute the modes directly from the stiffness matrix. That's known as modal analysis. It works, but you don't always have the stiffness matrix. So a trick that we found that works very well is you take your reference shape, because we are assuming we have a reference shape, and it turns out, I'll show this in the next slide, that if you assume that these lengths, the lengths of the edges, are forced to remain constant, this has relatively few degrees of freedom. You can show that in fact the number of degrees of freedom is proportional to the number of outside edges. And for example, you can parameterize this. Once you define the angles shown by the squiggly arrows, that completely defines the shape. Which means that given a reference shape like this one, you can create a database of feasible shapes by sampling this space of angles, which is not that big, and then do PCA on that. So two ways of generating this representation. You have a stiffness matrix. You just compute its singular, its eigenvectors. These are the deformation modes. You don't have a stiffness matrix. you do this trick.
This is a origami word problem.
I'm sorry?
This is a origami word problem.
It's a what problem?
Origami word.
Yeah, it is. In fact, it's funny. I mean, the reason we came up with this is, so this is a lot of work by somebody who's called Matthew Salzman, who's now a assistant professor in Chicago. And his mother is a high school teacher. And they use to teach in school, to teach kids in school about geometry, they have, it's not quite origami, they call polydrons. They are meshes made of plastic facets with hinges. And that's how we got the idea for doing it this way. Okay, and so for example, we did a lot of work at some point modeling sails from images, and we use that. So typically, because the sail maker gave us the model they use to actually, these things are made, you cut panels, and then you assemble the panels, and there is a model somewhere that was used to design the panels. So they gave us the model, we triangulated it, and we ran this procedure, and that gives deformation modes like this. And the important thing about this, again, is the red shape is not flat. It's just this bell-shaped thing. It doesn't matter. It changes nothing to the process. So once we have this, so let's go back to our problem now of we want to compute the shape of the thing, x, given the correspondence. We want to solve mx equals 0. And we know that x can be expressed as the rest shape plus the modes times the weights, and the a's are unknown. That's what we don't know. So we throw this into, we replace x by this, we get this, we add this, which w, which typically when you do modal analysis, you penalize the higher energy modes. So you can do that too. And what you get here is another linear system, except it's not in terms of the x's anymore, it's in terms of the modal weights. And you could say that problem is solved. Unfortunately, I don't know why that is, but it doesn't show, so you'll have to trust me. This matrix, actually, if you plot the singular values of it, well, they are still not all non-zero. Here, there's about 8 or 9 that are non-zero still. So there still is an ill-posed problem. So we didn't smooth to the point where we made it well posed, but we smoothed it to the point where there are now only 8 or 9 unknowns, which is a lot better than 1,000 or 2,000. And we can still we can still play the same trick. We can find a null space of this, write A as a weighted sum of the singular vectors, and write our inextensibility constraints in terms of the weights. They are still quadratic. They are now at 8 or 10 variables. So we can do what's called extended relinearization to solve this system of quadratic equation and get an answer. And so what we get is something like this, where, so the title is independent detection to mean that the computation is done independently in every single frame. There is no temporal consistency imposed, just to show you that the process is stable. And the difference here between these two views is, on the left is the raw output of what we do, and on the right is there is a nonlinear minimization afterwards to refine it. You can think of everything I've told you about as a DLT, a direct linear transform. It's well known that the direct linear transform is not precise, so if you want more precision, you do nonlinear minimization afterwards. And the same idea here, so you can see it quite well. The problem with the DLT is here it kind of vibrates. It's never completely wrong, but it vibrates because it's not very accurate in every independent frame.
How do you know it's right or wrong?
We've run it on synthetic data. Basically, it's really hard to get ground truth data for these things. But actually, I'm going to get back to that. There might be a solution.
You can film it from your point of view at the same time as filming the visual.
Yeah, we have to set up. We just didn't have the device to do this. So it's a matter of getting a structural light device, or several images.
Just get a second camera.
The second camera and do stereo, yeah. Yeah, yes. So instead, what we've done is we've used synthetic data, and I'll show that a little bit later. Okay, so that's nice. Well, I hope that's nice, but still, it's a little bit limited. And one of the limiting things about this is I've told you I want to make my surface inextensible. What does that mean exactly? In what I've shown so far, inextensible means that the distance between two vertices of the mesh remains constant. And that's not a bad approximation for something that doesn't deform too much. But it's a bad one when the curvature becomes high, especially when the curvature becomes high with respect to the distance between two vertices, because in something like this, even assuming that the material is truly inextensible, what's preserved is geodesic distance, not Euclidean distance, which was what I've been doing so far. So that's not quite right. And what happens, and I'll show this at least on the thick data in a moment, is that it introduces errors when the thing starts folding sharply. So that's the next part of the talk is, okay, what are we going to do about this? And so essentially, how can we handle creases and get this result where it actually creases reasonably as the thing deforms? And so the obvious thing that we could do is to say, okay, well, what I've just said is that the distance between two vertices in an inextensible surface cannot increase, but the Euclidean distance can decrease. So instead of being an equality, it really should be an inequality. So the naive way to solve the problem I've just mentioned is to do exactly what I've described so far, but replace the equality by an inequality. The problem is this is not quite right, because if you write it that way, you have all sorts of trivial solution because of the scaling problem. This, I mean, for example, x equals 0 is a solution. I mean, that's not quite right. So to make this work, you need one more thing. You need actually to push the thing away from the camera, so that what's going to happen is it's going to try to make as many of the inequality constraint equalities. You push it away, and some of them will remain inequalities. So that's, if for those of you who, like me, have some gray hair, that should remind you of balloon forces of snakes of old. It's the same idea, basically. So one way, so what we do, in effect, we're going to push the points along the lines of sight as far as the line constraints allow. And so, which means, instead of minimizing this, which is what we were doing before, we're going to maximize this, which is essentially an expression of each. This is a distance of the vertex, of the vertex of the mesh from the camera along the line of sight. And it is a linear term, minus what we were trying to minimize under the inequality constraint. And the reason we write it this way is because this is a convex optimization problem. So if it's convex, we can find a global minimum, or maximum in this case. And so that can work by itself. I'll show it in a moment. But in some cases, you have noise in your data. So you might want to regularize a bit. And because I want to be able to model creases, I don't really want to have a global PCA-style smoothing like the one I just showed before. So we replace it by a local smoothing. So what we do, in effect, is we take advantage of the fact that locally things may tend to be smooth, and we represent local patches in terms of deformation modes and penalize local deformations from these modes. And that actually can be expressed directly in terms of the coordinates of the meshes, so that we can add a regularization term that still is quadratic, and essentially says that locally, the local deformation should be small. Another way to regularize is to do temporal regularization. All what I've shown so far was done on a single frame. There's a single input frame. There's a reference frame and an input frame. But in fact, we're dealing with video sequences. So what we can do is work, say, on very short sequences, 3 or 5. Of course, I'm using odd numbers so that the middle is the one in which we're really going to compute the shape, and say that the motion is smooth. And actually, I think that's a more generally applicable constraint than the fact that the temporal deformation is smooth is more generally true than that the spatial deformation is smooth. So that's another way to do regularization, is to add a temporal constraint, which also is going to be quadratic. And so we did try to validate this. And the way we did this is we used optical motion capture. So we took several materials to get natural-looking deformations. We pasted Vicon targets and waved them in front of a Vicon system to get the 3D position of those markers. Then we texture map these things and compute correspondences between the images to see how our algorithm behaves. And here's the kind of result we get if we use, say, SIFT Correspondences. So this is the number of frames. This is the error in millimeters. So it doesn't really, I mean, the absolute number doesn't matter all that much. What's sort of interesting is the different behaviors of the algorithms, the comparative behavior of the algorithm that I presented. So what happens in the sequence, actually, it starts not very deformed. In the middle of the sequence, the deformation is strong with a lot of creases, and then it's less deformed towards the end. And when you run the version of the algorithm that uses equality constraints for the length, so the first half of the talk, you get this kind of errors. When you run the algorithm with the inequality constraints, you get this. So the errors are a bit larger when there's a lot of deformation of the creases, but you notice there's a fairly significant improvement with respect to the equality constraints. And in this case, because our surface is well textured and the SIFT correspondences are pretty good, adding the regularization term doesn't do much. I mean, it helps a little bit, but it's not very significant. And that's a fairly generic behavior that we've seen on many, many examples. I'm sorry? So the red curve is what we get without any regularization, just by without regularization. So without any. So I've told you the two kinds of regularization that we have is either a local shape ball that saying that the surface is locally smooth, or that the motion is temporally smooth. So there's two ways we can do it, and in this particular case, in the case of the red curve, we do neither. In the case of the blue curve, I think it was, well, actually it's said it's the shape, we use a shape regularization. Now, of course, where regularization is important is when we start having outliers. So let's say that we start putting in, okay, we have our good SIFT correspondences, and we start introducing outliers and errors. And what you can see is that if you don't regularize, which is the red curve, up to 10% is sort of okay, and then the error starts increasing. If you regularize, then you delay the onset of trouble, and you can more or less deal with about 30 to 40% of outliers with this algorithm. Now, this is the same, essentially the same thing, except what we are comparing here is using, instead of using shape regularization, we use temporal regularization. And what that says essentially is, if you have temporal regularization, you don't really need a shape regularization, because with and without it, essentially the same curve. So essentially, you use one or the other, whichever is more convenient for. I'm sorry? On the right, so we have temporal organization. No, the label is right because it's shape. It says temporal is here, but in one case we don't use the shape in addition, and in this case we use both kinds of organization. Sorry, is it?
Single frame, multiple frame. That's the key.
Right. Yeah. Yeah. So this is strictly single frame. This is multiple frames. Okay, and so when you look at it like this, this is what it does, and the best you can do is if you regularize temporally, and you get something reasonably smooth on that cushion. And this is another thing where we track the T-shirt.
So there are some parameters that are determining relative weights and stuff like that.
Yeah, but there's one weight which is the relative. Yeah, there are a few there, of course. There is the weight of the balloon force,
Right.
how hard you push, and then how much organization you put. I think they are the two fundamental parameters.
Them and they seem to generalize across different fabrics and different things, or
They are reasonably stable. I wouldn't claim that there probably was a little bit of tuning somewhere. But Mathieu didn't spend hours changing them on he didn't change them for every different experiment. And actually, you could of course learn them, which would make sense. Okay, so so this essentially what I've shown so far are cases where essentially you gave as input correspondences. You gave a reference frame, you get a bunch of correspondences. What I've shown is from this, you can recover the shape. But of course, you can't always establish correspondences. And one case where establishing correspondences is hard, for example, is if you have repetitive patterns. So this is the reference image. This is the reference image. This is the input image, and if you run SIFT on this, you're going to get strange results, or most anything else, presumably. So one solution to this is to say, okay, fine, I'm going to try to establish simultaneously the correspondences and compute a 3D shape, as opposed to do it sequentially. And essentially, we got this idea. I think Torresani gave a talk at one conference where they were doing that sort of things in 2D. So essentially, this is an extension of that style of thing to 3D. And so the problem that we're now going to try to solve is to minimize a score that essentially is the same as the one we are having, but where in addition, essentially the correspondences are not fixed. So one point can correspond to several other points, so we have our M matrix has more rows, but these rows have weights. Essentially the weight has to do with how strongly you believe that a particular correspondence is true. Since a point can, of course, correspond only to one in the end. And you do an optimization, you do a minimization where you try to estimate at the same time the weight of the correspondences and to minimize the residuals. And essentially what this is, in theory, it is an NP-hard problem because technically it's called, so we have a quadratic problem, which is what we were trying to solve before. You have the integer problem, which is to decide what corresponds to what. So that's a mixed integer quadratic problem. And what we did was to develop a branch and bound algorithm that actually solved this. And does something like this, where we get this kind of a result here on this shape. So if I show you what it does on the cushion, it does a reasonable job of it. But of course, it's a lot slower. Computing each one of these frames, I think, was half an hour. So we are kind of not quite at the real-time level. Okay, And the final thing I'd like to show you, maybe more as future work than anything else, is, okay, this is good, but of course one fundamental limitation in all of this is I need a reference image. I have assumed I have a reference shape and a reference image. I may not always have it. So can I extend these kinds of technique to this the more general case where I simply have a video and no reference? And the answer is probably yes. And here is the first try at it. So now I still have my input frame in which I want to compute the shape, and I have what I'm now calling a support frame, which is just another frame in the video sequence, but not one in which I know the shape. There is none. So I have these two shapes, and what can I do? So of course this is not stereo, because the shape has changed between the two frames. So what I can do is read Andrew's book carefully, and assume that things are locally planar, meaning that I can take my image, I can break it down in small patches, and within each patch I can assume that the thing is roughly planar, which means I can compute a homography. So I can compute what these things represent here is, so I take my two frames, I establish correspondences, I break the image into local patches. Within each local patch, I compute a homography from the correspondences, and that gives me this. And of course, every homography allows me to compute actually the 3D coordinates of these points, but only up to a scale factor. There's an unknown I cannot resolve, is how far they are from the camera. So I get these disjointed patches, but I know, or at least I'm assuming, that they all belong to the same surface. So having done that, I can adjust the distances of every single patch so that the points essentially that belong, my patches are chosen to be overlapping, so that I have points that belong to several patches. So I can actually adjust the distances to the camera so that the points that belong to more than one patch are consistent from patch to patch. I get something like this, and I fit a shape. I fit a surface to this when I'm done. And the kind of result I get is this. So here are my patches. Here are the points. The red points are the ones for which I've established correspondences. And what this process does is transform these correspondences into a bunch of 3D points to which I can then fit a mesh if I want to. And here is the kind of result I get for this image. So it works, but of course, because there is this local planarity assumption, there's no way to deal with really sharp deformations. So that actually is the next step, I think. And I believe there is a recent ECCV paper where people do something like this. Is maybe one idea to go further is to replace the planar parameterization by, say, quadrics or something a bit more sophisticated, so that we could handle bigger variations within the patches. Okay, so that's essentially what I wanted to present. And actually, at this point, at some point, we were relatively happy. We wrote a little book, which actually is a tutorial on this, which summarizes some of these things. And then it's fitting that I would present this at Microsoft threw a monkey wrench in the works in the forms of this horrible thing. Well, I don't know if it's, I know it's horrible actually. It was pretty impressive. Last week before I left, I mean, there were two of them. I was a group of people looking at the Kinect and playing with it and trying to understand how it works. So I don't know, on a sample of 20 graduate students, I don't know if that's representative, it's a major success. But anyway, so a question actually that we've been wondering about is, now that this exists, is there still any point in doing this? It's okay, it's published, so we can move on and do something else. Or we can also actually apply some of the techniques I've described for inextensible surfaces to the output of the Kinect, which is something we're going to do. And we can also argue that, fortunately for us, there are still a few applications for which being able to do it just with a webcam has merit. And so here's an example. This actually is a bit different because this deals with rigid surfaces. But what this is, so this lady is a graphics designer who took some of our algorithms. She hid the camera in the lamp. And the camera is looking at the book. And what's, I don't know if you can see it, but it essentially registers, it sees where the book is, and then it can augment the pages. And so apparently to her, it was very important that the camera is not visible, that it's hidden. And of course, so this actually, again, works with rigid transformation, but it could be made to work with what I've just shown with the deformable thing. And actually, she went to a different art show where she played with the same idea. The camera is still hidden in the lamp, but now she's playing with this cushion, and the thing is computing the deformation of the cushion, and then she has a clever way. I mean, she interacts with the computer by deforming the cushion. Whether that's useful or not, I don't know, but it was kind of fun. Another thing where, again, is it useful? I don't know, but it's really a lot of fun, is we are lucky enough to work with people who design boats, and especially fast sailboats. So we've been working with this guy. This is actually a cool thing. This is so this is a sailboat that is on what's called a hydrofoil. So which means when it starts going, it lifts out of the water. The hull does not touch the water anymore, and it goes incredibly fast. They actually hold the world record at 51 knots. So for those who sail, that's really, really fast on a sailboat. Anyway, so that's cool, and we've been working with them to essentially have the system, and the system is looking at the sails and measuring how it deforms in real time. The idea being to analyze how the sail behaves under real sailing conditions, and perhaps also, that's longer term, but you could imagine have some kind of an automatic pilot that would look at the shape and then fine-tune the sail based on these real-time measurements. And actually, I kind of like this. I mean, I don't know if you can see this, but the sun is shining. There are all sorts of reflections, specularities, all sorts of things that would make life hard on the Kinect. So, thank you. And I also kind of like planes. So, the wings of planes deform a lot. Actually, next time you take a flight, sit by the window and look at the tip of the wing. Even on a real airliner, it moves quite a bit. And we actually want to measure this precisely because, of course, the plane, the wings have been designed to move in a certain way, but at some point you do want to check that the way they form is the way they were intended to. And so we are actually working with, so of course this is a glider, so there is not a big commercial market for this, but there is a big commercial market for this. We're working with a French aircraft maker called Dassault, and this is the wing of one of their latest business jets. And actually these wings are very thin so that they don't drag too much and so that you don't consume too much fuel, and therefore because they are thin, they deform. So there is really a real point, commercial interest in doing these things. And this is actually the one thing we probably won't do, but I thought that was very cute. So it was mentioned that I used to work for SRI in California with some unnamed three-letter agencies who were interested in what we did. And I talked about this with the head of the AI center. Say, oops. Oh, thanks. So I talked about this to the head of the AI center. Who said, "Well, this is cool. I have an application for you. Could you use your techniques to look at these banners and unfold them so that we can do optical character recognition on them? And I think and you can guess, I think, why three-letter agencies might be interested in this. And the answer is yes, you could use this. But then I'm very happy, I'm in Switzerland, I don't have to do it. I can keep on working on the sailboats. But the technology is essentially the same, of course. And one other one... Yeah.
You don't have the boundary, would you?
I'm sorry?
The only information you have is the boundary shape.
No, because since they are banners, for example, the late technique was you would have the interest points on the characters.
You don't know, I mean, the point is to read it, so you don't know what the...
Yeah, but the last technique I've shown you does not require a reference image.
In a sequence.
In a sequence, yeah. Yeah. You would have a video, you'd have a... and of course, that's a good point. I have not said anything about using edges, but of course, you should use them. And that's also on the agenda. Sorry?
Would you have to do segmentation even for the sailboat? Did you do the segmentation for the sail?
No, because we have interest points that we can find, and we have for the sailboat we have the model of the sail. Here we don't. So yes, you would have to do the. I mean, this technique by itself would not be enough. You would have to do a whole bunch of other things, but this could be part of the solution.
You segmented this by hand. Is it easy to try on some of this?
I think it would be relatively. Yeah, it would be easy to try, I think. So we could, yes. And one other thing that we haven't tried, and that's actually just a thought, is in modern surgery, there's a lot of laparoscopic surgery when you insert a small camera in the body. And apparently, one of the problems is I mean, I imagine surgeons would never confess to that, but I think nevertheless it is disorienting. And having something that finds its position, slam, or computes the shape in real time within the body would be of use. So I would not trust the current algorithm to this. I mean, if a surgeon tells you he's using this, go somewhere else. But still, it is a potentially interesting direction in which these kinds of techniques could be applied. So all of this to say that even though there are things like the Kinect, and there will be more of them, I hope and I think that there still is a room for these kinds of techniques that are extremely lightweight and will work with them basically with the small cheap cameras that's available everywhere. And of course, that's what I've presented here is the work of a lot of people, and especially the people whose names appear in bold faces. I mean, this is 2 or 3 theses worth of work. So, thank you.